Hello, my name is Alejandro Ojeda, and today I'm going to be talking about my Lab 3 black holes. So, this is the key concepts that we need to be introduced. The Newton's law of the first law of motion, which is what stays in motion must stay in motion until another force acts upon it. We also need to know Newton's second law, which is F net. It's equal to the change of momentum divided by the change of time. We also need to know the kinematic formula and the velocity formula so we can find the position and velocity of the objects that we're looking for. We will also need to know about centripetal force, which is the mass times velocity squared divided by the distance. We also need to know that the net force is the addition of the parallel force plus the perpendicular force. And finally, we need to know the F of g, or the force of gravity, which is equal to the negative of the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them raised to the power of 2. And for this, g will be 6.67 times 10 raised to the power of negative 11. So this slab is divided into two. So for the first part, the system will be the star, and the surroundings will be the black hole in space. For part two, the system will be the ship, and the surrounding will be the star or planet, however you would say, and the black hole in space. The goal is to find the mass of the black hole, and for part one, and for part two will be the find the initial velocity needed for a spaceship to fly around the black hole without crashing on the planet or black hole. So here's the first computational models that were used to get the results for part one. Most important is to note that the net force is just the derivative of momentum with time. And then here in part one, here we get the results. The magnitude of F net, which is 8.74 times 10 to the 28 newtons. Magnitude of F net parallel, which is 2.98 times 10 to the power 27 newtons. Magnitude of F net perpendicular, which is equal to 8.74 times 10 to the power 28 newtons. And the mass of a black hole, which would result in 1.3 times 10 to the power of 34 newtons. And with this, we get that it is an elliptical orbit, but we know that there might be possible errors for me because the black hole mass was an approximation, and so was the g constant. Now, for part two, this will be the the coding that was used. The most important part will be that f of g, the formula, was used extremely here, as seen on the second image to the right. And here is the results of part two. You get that the initial velocity is a vector of negative 4.8 times 10 to the power 7 to the x-axis and 1.7 times 10 to the power 6 to the y-axis, meters per second. The distance from horizon is 1.59 times 10 raised to the power 11. And the planet's orbital speed is 9.33 times 10 to the power 6 meters per second. The planet's orbital period will be around 1.87 hours. And some possible errors that might have come to this would be like the launch angle was not accounted for, therefore it could have some discrepancies in the result. And there might be a possible input error on initial velocity, meaning that I might have not calculated that right. So what does it mean? F net and rate of change of momentum are basically identically mathematically. So F net is just the mass times acceleration, which is equal to mass times velocity divided by time. While rate of change of momentum is just delta p divided by delta t, and then that will simplify to mass times velocity divided by time. In this experiment, use rate of change of momentum because we do not know the mass of the black hole. And for what ifs, we figure like if it's possible for a spaceship to be in orbit. It is possible. With the speed on the x-axis being 9.9 times 10 to the power 4 meter per second, and for the y-axis 1 times 10 to the power 7, the spaceship is possible to get into an orbit uh, and go around the black hole without crashing in either the black hole or the planet. Thank you so much.